Okay, so thanks. In the next hour-ish, I will continue to talk about neutrinos. This is my second half. Okay, so yeah, before I go to the next page, so this talk will be mostly about the JUNO experiment as an example to show you the challenges of such big experiment and what's the physics target we are going to achieve. And then in the last part of my talk, I will talk about some prospect about the neutrino absolute mass measurement, including cosmology, the double decay, and the beta decay. So I hope I can finish in 1 hour and left you some question time. Okay, so this show you a mass spectrum for all the leptons and quarks. At the end of previous talk, I was asked about the hierarchy concept. So in this plot, you can clearly see the hierarchical structure for quarks and the leptons. And you see these generation 1, 2, 3, and their masses are like clustered in different categories. So this is obviously a hierarchical structure. But for neutrinos, we don't. They are all very small. There's no real hierarchical structure from my experimental point of view. So now we call it mostly neutrino ordering. And the absolute mass of the lightest neutrino is unknown. This is a new one. For nu 2 and nu 3, we using oscillation measurements, we know the mass square difference. So we kind of know where it is. But the exact order of 3 and 1 is the problem we are going to solve. And also whether neutrino are its own antiparticles. This will rely on the neutrino instability decay. So in this plot, you see a desert in the middle. So we don't know why the nature gave us this structure. But in any case, we need to study the properties of neutrino masses. Okay, so for mass ordering, yeah, as I mentioned, this talk will be mainly about JUNO, and JUNO use reactor neutrinos to determine mass ordering. So looking at this formula, you will realize that it's almost a vacuum oscillation with the reactor neutrinos. It's provide a unique and a complementary method compared to the accelerator and atmospheric neutrino experiments to determine the neutrino mass ordering. And these are the term related with the neutrino mass ordering. And this show you the oscillation spectrum. This is energy, and this is the event number. And this is a long oscillation spectrum. And for normal and inverted ordering, you see this blue and red wiggles. This is a small oscillation pattern. And from data, we'll try to test which hypothesis is correct. To do so, we need a high energy resolution to be able to see this small oscillation, these small wiggles. And once you have this precision measurement of this oscillation spectrum, of course, you can precisely determine theta 1, 2, the large oscillation amplitude, and the oscillation frequencies, the delta square 2, 1 and delta square 3, 2. Why I said it's complementary to accelerator and atmospheric neutrino experiments? Because reactor neutrinos is kind of measure the interplay between two mass square difference, these two. And the other experiment measure a different effective different effective mass square difference. So you can see here. And the difference of these two delta square EE, delta square mu mu, the difference will further enhance the neutrino mass ordering information. So our very early try is back to 2008, 2009. At that time, we are even working on the Data detector construction. So at that time, we are start to think about what's the next future, what we are going to do after diabase. So we are considering the diabase 2, whether we can use the reactor neutrinos to determine neutrino mass ordering. And then we did a simple analysis. We do a Fourier transform to transform the oscillation spectrum into frequency domain like this. And we observed that for normal ordering and inverted ordering, which is in solid line and dashed line, these two scenarios, we found a very interesting structure. For normal ordering, we first see a peak and then see a valley. And for inverted ordering, we look to the left and first a peak and then a valley. So this is a very simple and obvious feature that we can use. So we develop a simple discriminator according to the peak to valley ratio and the position of peak valley. In the end, we have this discriminator, and it shows a good discrimination power between normal and inverted ordering. And based on this, we did an experimental test to figure out what's the experimental requirement for us to do diabase 2 experiment. At that time, we don't know the θ13 value. 2008, everyone thinks it's small. So we did a few tests. The largest value we test is this one, it's 0.09 θ13 term square, sine squared 2 θ13 value. But it turns out this is probably the right number now, but we don't know yet at that time. And with these parameters, we came out with the idea for diabase 2 that we need powerful reactors, 36 gigawatt, and almost 60 kilometers baseline. We need a 20 kiloton liquid incinerator and a good energy resolution, about 3%. So this is almost exactly the same key parameters for now JUNO experiment. So that was determined very early in the diabase age. But of course, later we did a more sophisticated chi-square analysis to well study the sensitivity to optimize the different parameters. Now the JUNO Jiangmen Underground Neutrino Observatory is here. It's in South China, close to the sea. And we have two nuclear power plants here. It's Liangjian and Taishan. They are all powerful. And our JUNO detector is almost at the center of these two reactors, and with the equal baseline to the two reactors. The reason we put the baseline around 52 kilometers is that this is a maximum oscillation for θ12. So in this case, we can have a better sensitivity on the small oscillation. And very interestingly, we found that we really should have an equal baseline to two reactors. Otherwise, the oscillation will be kind of canceled. So in this case, the baseline difference between these two should be less than a few hundred meters, 500 meters. And if you remember that the success of diabase is that you will have a good mountain coverage to suppress the cosmic ray background. So in JUNO, we need the same thing. So you need to find a place you have mountain. You cannot create a mountain, but you need to look for some mountain area to build your detector. And you also need to consider the cost. Most likely you will dig a tunnel or a horizontal tunnel or go deeper underground. So it's very expensive to do that. So you need a good condition of the rock. So the granite is the perfect rock. You can easily do the tunnel. So with these two constraints, we look at this area. This is probably the only place we can put our detector. This huge granite rock area is here, and this rectangular box is that we have to put our detector somewhere here to meet this requirement. So in the end, this is the only place we can do the JUNO experiment. So that's the optimal location. And this project was proposed in 2008, approved right after the discovery of non-zero 613 in 2013. And sorry, this is kind of old. We are not super old. Our detector completion was end of last year, and now we are doing the scintillator fitting, and we have reached physics goals, which I will cover later. And this is the surface building of this JUNO experiment here. This is the entrance of the slope tunnel, 1.3 kilometers tunnel with the slope of 40%. It's kind of a deep. And this is our detector under this hill, small hill, not very high, like 280 meters high. And so we need to go underground by another 480 meters to have enough overburden to suppress the cosmic rays. And the civil construction was finished in 2021. This is a detector, how it look like. Now to have sufficient statistics, we need 20 kiloton liquid cylinder here. This was contained in a world's largest spherical acrylic vessel. Diameter is 35 meters. And this whole detector was merged in a 35 kiloton water shielding to control the radioactivity, to suppress the radioactivity from the rock. And we have more than 20,000 large PMTs, 20-inch PMTs, to guarantee the good energy resolution. And the PMT's efficiency was high, the best in the world. I will also cover all the details later. So in this talk, the first half will be mostly on detector design and the challenges. So it may be a little bit technical, not so many fancy physics. But that's the key, that if you do want to do good physics, you need a good detector. And you have to consider all the challenges, all the difficult aspects to make your detector to be good. Okay, so that's in the next 20 or 30 slides, I will show how we make this detector. Let me start from outside to inside. So first, the water pool. So this is a central detector, and it emerged in a big water pool. The water pool is 44 meters height and 43.5 meters diameter. And this water pool, as I said, will provide passive shielding of the radioactivity, and also it's equipped with the PMTs to be an active water Cherenkov detector to actively detect the mirrors. And you require a very high efficiency for the mirrors, so you can further reduce your background. And the whole detector should be maintained in a very stable temperature situation. Otherwise, the structure, due to the thermal expansion, the whole structure will not be stable. So 21 degrees, the plus minus 1 degree is the requirement. And also, we need to remove the radon in the water. The radon is a bad thing for the low background detector, so we have to remove it. And also the transparency of water for such large detector should be very high, more than 6. Now 6 meters is our measured value. It's even better than that. And also the 20-inch PMTs can be easily affected by the Earth's magnetic field. So we have this coil surrounded the whole detector to produce a field to compensate the electromagnetic field from the Earth. So in this case, we can have a good performance and uniform performance of PMTs. Now, the first question when I was first involved in this experiment, I was charged to optimize the the water pool dimension. Again, so this is an example to show you how we consider all different aspects. So the water pool, as I said, it provides the shielding for the gamma ray. So you need a minimum thickness, and also to guarantee the muon efficiency at the equator. So you have a minimum thickness here. And we have a lot of materials here, the PMT signal structure, etc. And we need to control the reactivity budget. So we need to evaluate the sensitivity as a function of this thickness and to scale it to the project cost following the merits. In the previous talk, I already mentioned that we are scientists, we are experimentalists, we need to use a minimum money to achieve the greatest physics. So cost is always the factor. So here, if you scan this parameter and you realize that your best the thickness is here. So that's first example how we determine the size of the water pool. There are many other challenges for the whole detector. As here. First, the whole cavern is very large. It's one of the largest underground cavern in China. And the first challenge is to make this 35-meter diameter acrylic sphere. And this acrylic sphere is supported by the stainless structure. I can move to next slide to show you. So actually, in the beginning of JUNO, we talk about 4 options of a central detector. One of the options is to use balloon. If you know the Neutrino experiment and the Cameron experiment, they use balloon to contain their target. So in the beginning, we also considered balloon. But imagine that you need to build like a 20-meter diameter, 30-meter diameter balloon. It's very difficult. We make a 12-meter diameter balloon prototype, and we blow it in our experimental hall to test the strength of this balloon and measure the transparency. But in the end, we figured out the acrylic sphere was the more safer and robust than balloon. And it can have a better background condition and longevity. So this acrylic is supported by the stainless structure. And you see these many pieces, more than 200 acrylic vessels, and largest one is in this dimension. And we have close to 600 nodes to hold, to support this stainless structure. And these pieces actually are, the whole sphere is made on-site by polymerization using these big pieces. I will show some plots later. And the supporting structure, each of them should have very good mechanical strength and reliability to allow you to be, in operation and in the filling, the mechanical situation is very complex. There are many key issues here. We have more than 20,000 PMTs. The clearance between each one is 3 millimeters. This is a huge challenge. I will also mention this later. And the whole structure, we don't require welding because welding always brings reactivity background. So these are like logo. How do you say? Look, there's a for kids. There's like a how to say? There's a company produced the small how to say? It's like you make for kids. You use small pieces to build your tool. Lego, yes. It's a similar way. Like we build this detector, we make it like a structure and no welding, and you piece by piece do it. Yeah, and as I said, temperature control, and also you need to consider the earthquake safety, and acrylic quality and strength, etc. So I'll show you some pictures. So this is the stainless steel structure. This should be a very precise structure to be able to realize the 3 millimeter clearance between each PMT. So this whole structure should be very precise. And with 120,000 sets of bolts, we collect all the different pieces into this big structure. And the overall deformation is in good shape. It's just a few centimeter, like 20 millimeter deviation from the design. So it's a precise, gigantic structure. And then how we make our acrylics fail? In this way. So the whole structure, the stainless steel structure, is constructed from bottom to top, like a Lego. You can from bottom to top, and the acrylic vessel is made from top to bottom. We have this installation platform, layer by layer. We have 23 layers. So from top and to bottom, you bond these acrylic pieces into a circle, and we do it simultaneously. Like many pieces are bonded simultaneously in one circle, and you layer by layer. And this show you the stainless steel struts which support this. And this platform is big to hold many equipments. This acrylic vessel, as I said, is more than 200 pieces. And this is the world's largest acrylic vessel. The thickness is 120 centimeter. Sorry, 120 millimeter thickness. So if you calculate the ratio of the thickness to the diameter, it's even thinner than an egg. Well, we eat egg for breakfast. The egg, if you calculate the ratio, this one is even thinner than an egg. So you can imagine how fragile and how difficult to control it to be stable. And we need ultra clean production. This 600 tons of acrylic, the reactivity of the uranium and thorium should be less than 1 ppt part per trillion. And the transparency should be very good, more than 96%. So the technology, bonding technology I already mentioned, is very clever. So they use a special bonding technique to bond the T-shape. As you can see here, this T-shape, to do it simultaneously in one time. Otherwise, it will be very time-consuming, and the stress of this acrylic is very difficult to control. So compared to the previous snow experiment, the diameter is, for JUNO, the diameter is 3 times larger, weight is 20 times larger, the bonding line is 4 times larger, 2 kilometers of bonding lines, and the thickness is larger. So the difficulty is way more, 1 order of magnitude difficult. So, and we need to finish it in 1 year. Well, we are a little bit delayed, but roughly in 2 years. And here we also use plastic to cover the surface to protect the radon elimination into the acrylic. The radon is a bad thing for the low background experiment for us. In the end, we successfully completed the whole construction. And this is another plot to show you we are close to seal the bottom part of the acrylic vessel. And another challenge is the 20 kiloton liquid cylinder. We need the transparency to be very good, better than 20 meters, and the reactivity is less than 10 to minus 17 gram per gram. Well, this probably is not easy to understand, but imagine that this requirement is equivalent to, in 20 kiloton liquid centimeter, your dust should not more than 10 kilogram, so not more than 10 milligram dust in this 20 kiloton centiliter. So this is another huge challenge to make this pure centiliter. And the first thing we are facing is that to optimize the recipe, we have a good experience on diabase, and this is the requirement I already mentioned. And the good thing is that when we start JUNO, the diabase is still running. So in the diabase experimental hall, we build a pilot plant to test the purification system and to use one diabase module to even test the recipe, the different recipes of the centiliter to maximize the photon yield in JUNO to reach the resolution goal. In the end, we use the measurements and using a new optical model I will introduce in the next slide, use a new optical model to optimize the recipe for JUNO. It's here. And now we are in the production phase. All this solvent transparency and the transparency for the final product and the reactivity of the fluors all meet our requirements. So this is good. We can maintain our low background. And let's show you the measurement and the Monte Carlo comparison. This model works well, and our recipe should work. And this is some details about new optical model. I started this work when I was a PhD in 2009 or something. But at that time, I spent a lot of effort to measure the optical parameters like emission spectrum, absorption length, fluorescence content yield. But I did not have a chance to validate this model. I read this model in my PhD thesis, but without real good data to validate it. So luckily in 2017, we used one diabase detector module and eventually validated this model. So I was happy that this small piece of work lasted for 10 years, almost, and it finally worked out. This diagram shows you this model can describe the absorption and the re-emission of the photon between the three components, the solvent, the fluor, the primary fluor, PPO, and the wavelength shifter. So it's a complex model and a lot of optical parameters, but eventually it works. Another challenge is the PMTs. So this picture shows you the installed PMTs, 20-inch PMTs. It's quite dense, and these are the supporting bars. The first thing we require to our 20-inch PMTs is the photon detection efficiency. We need as high as detection efficiency as possible to guarantee the photon yield, to guarantee the energy resolution. So the R&D of this new type of 20-inch PMT, so-called micro-channel plate MCP PMT. We started this, actually it was Yifang who established this collaboration with industry companies and the institutes to start this R&D in, again, way back to, started from 2009. At that time, we discussed about diabase 2, and we realized that we need a new type of PMT to have a high efficiency to guarantee the energy resolution. So this have many years, almost 7 to 8 years development. Finally, we achieve a very good energy, very good collection efficiency, content efficiency, low background glass, etc. I even go to the company to supervise the company to make the glass bulb to make sure it's low background. Maybe I have a picture later. We keep improving the efficiency from here, like 27% to 29% and to 34%. This is a pure content efficiency, but you also need to take into account the collection efficiency. So eventually we select 3/4 of MCP PMT and 1/4 of dynode PMT. And the production for dynode PMT, they are stable, but for MCP PMT, the company is very collaborative. We are keeping improving the efficiency, which is good for JUNO. So this shows some picture, just briefly mention what are the key components to develop this new type of PMT. First, you need, well, it's a secret of the company to make a special recipe for the alkali photocathode to reach more than 30% efficiency. And then we do the atomic layer deposition, ALD, surface doping, to increase the efficiency, detection efficiency of secondary electrons. So in this case, you can improve your photon electron detection efficiency. And this is the large glass bulb. There's only one company in the whole China can blow this thing. It's purely made by single-handed person. And there are two key persons finish this 2,000, almost 2,000 blobs. We searched the whole country, the no background raw materials, from the quartz, the silicon dioxide powder, and also the other component for making glass, the boron acid, something like that. And yeah, we almost searched the whole country to find the proper vendors to make this recipe, and finally make a very low background glass bulb, which is a factor of almost 20, then lower than Hamasu one. So this was a great success. These are the special steps to make this MCP PMT. You have to seal the vacuum, use COVA and glass collection, and this is the machine to evaporate the photocathode onto the inner surface of the PMT, and this is the final product. So this was a great effort. And how to choose the PMTs? I would like to use this as an example to demonstrate how we to reach every extreme to maximize our detector capability. Now we have two types of PMT. So may I ask a question to you guys? How you make your choice? Which PMT to buy what fraction? They have very different characteristics. How to make this choice? So the question I was charged when it was back to 2015. When I was the physics coordinator of JUNO, and Yifa asked me, oh, please think about how to make your best choice of these two PMTs, considering the performance, the physics performance, the cost, and also the risk. So I come out, under his suggestion, I come out a quantitative approach to select these PMTs. This is the diagram. Three factors: the merit of physics, evaluate the impact of each PMT parameter on the energy resolution, the background, and eventually to the sensitivity. So, and then you have to scale your sensitivity into your project cost. You scale it to equivalent change of a target volume, and then you calculate the cost. So, and of course, the other factors. So this is how we exactly do it. This is a table. When we do the PMT bidding, the specifications and the characteristics of different type of PMTs. This is the detection efficiency, the TTS, the transit time spread, good for energy, good for vertex reconstruction, and the dark count. We expect a lower dark rate and lower pre-pulsing, after pulsing, and we expect lower reactivity. So the blue colors are what we hope. But you realize that the blue colors are not concentrated on one type, but on different types. So you have to balance the best choice. So I came out the calculation to evaluate each factor on energy resolution and then turn it into sensitivity, and then use this sensitivity to transform it into a cost. The same thing for the background. So in end, it's an analytical formula which you can judge which parameter is good for physics, and then you calculate the cost of cost change of your liquid centimeter, your acrylic vessel, the number of PMTs, thickness, structure, and even you need more excavation to make a detector larger. So in the end, we use this in our bidding documents, and probably the first time we use analytical performance calculation to finish our thank you. Okay. Yeah, to finish our bidding, and we have in the end this is results. We have more than 15,000 MCP PMT, 5,000 Hamasu PMT, and the photon detection efficiency is good. And moreover, we have these 3-inch PMTs in interval space of different PMT. I will also talk about later. So this is, I think, a good example for physicists, for experimentalists, for students or postdocs. How you think you will optimize your detector to have a best physics performance to reach your physics goal. This is one example. As I said, we have a small 3-inch PMTs to allow dual calorimetry. And these small-inch PMTs can help us to control the nonlinearity of the large PMTs. So as I said, we have very small clearance between the large PMTs, like a less 3 millimeter clearance. And around the one large PMT, you have 6 positions can put your small PMT. So this is what it looks like. But due to budgets, we don't fill each position with one small PMT. In the end, we have 25,600 small PMTs, which is a good coverage of all these spaces. And this is the picture on the top of our detector, and this is the top chimney. I have a movie on the next slide, so it's quite slow. So you can realize that the clearance is so small that we have a very risk issue, that the chain implosion. So this was happened actually in the Super K detector in 2001. Due to some reason, one PMT exploded, and the implosion happened underwater. Later on, well, a couple of years before, I talked to Super K friends, and they told me a story that someone who is really on site, and they really use their ear to hear a firework sound. It's a low voice sound. They really hear the boom, like this sound, and this implosion has destroyed 7,000 PMTs, and they have to reinstall their PMTs. But their density is 1/2 of JUNO, so we have like 78% coverage. Their coverage is 40%. We are even more risky than Super K. So we have to add a protection cover to prevent the shock wave generation. So there are a lot of interesting tests in this design, and I show you, well, this is actually 2 movies, but this doesn't work, I don't know why. But this show you how the shock wave generates and how it destroys the other 2 PMTs. So we use a stainless steel to hit the middle PMT to make it break. And you see this high-speed camera to record the water quickly go into this vacuum space and generate a shock wave, and shock wave will propagate to the nearby PMTs and destroy them all. So if we don't have this protection cover, if one PMT due to some reason was break, then it's a disaster. And we came out a critical cover design with various thickness and different locations with holes. And later on, if I upload the slides, you will see this protection cover. Even the PMT inside is broke. The cover stays. So in this case, the water slowly go into the vacuum and the shock wave will not generated. So the other PMTs are safe. So this is a very interesting but very important design to make our detector safe. So in the end, if I go to the previous page, in the end, all the PMTs have this protection cover. Okay, so the electronics, we have 20,000 channels. Each have like 100-meter long cable from different locations to our electronics room here. We have a high dynamic range, low noise requirement, and also the resolution for single photon electron detection is 10%, and we require a failure rate over 6 years less than 0.5%. This is actually a not easy requirement on reliability. So the solution is that we use 1 gigahertz flash ADC in an underwater box to read out all the full waveform readout from each PMT. So in this case, we can do our offline analysis to reach best charge reconstruction and the best energy reconstruction. And this one underwater box will serve 3 PMTs. And this is our commissioning test results. Our noise level was very good, even better, a factor of 2 better than design. It's 0.05 photon electron per channel. And for small PMT system, I already showed this picture before. We have almost 260,000 3-inch PMTs. And this will give 3% more light and help us to control the nonlinearity of large PMT. And again, the electronics is in underwater box to waterproof. And it's not a waveform readout, but it's like a ping pong photon counting mode. So you just count how many photons you receive, and then it's easier to analyze. And all the test performance looks good. Now we are commissioning this in our detector. So here I show you some plots, just to give you a feeling how we make this detector. The stainless steel structure, as I already mentioned, from bottom to top, like this way. And this is the installation platform for acrylic vessel. So layer by layer, we made our acrylic. And this is to the very bottom. We seal the bottom part with the chimney. And this is the final step. We check the outside of the outer surface of the acrylic vessel to put an epoxy layer to protect to further strengthen the mechanical strength and to reduce the stress, to reduce the risk during filling. And a few workers go around all these 2 kilometers bonding lines. It's not an easy task. And this is finally how we automatically clean clean the inside. Yeah, sorry, it's a bit noisy. Okay, anyway. It's an automatic nozzle to do a 3D cleaning. And before this cleaning, we even have a very good strategy. Okay. We even have a strategy to let the dust to fall down and remove it away. We spend a few days to settle settlements inside to do some moisture inside to absorb the dust, and then they fall down. They don't attach to the surface. And remove the protective film, as I already mentioned. We have the film to protect the radon, but in the last minute, we should remove this film and wash the acrylic surface internally, and then fill the CD and the water pool with the high purity water, and then replace. First, we fill the whole thing with the ultra pure water, and then replace the center with the liquid designator from top and remove the water from bottom. And all this radon and radioactivity control is not easy, but we finally accomplished that. And the final filling speed is like 7 cubic meter per hour. So 2 months for water filling and 6 months for centimeter exchange. So now we are almost here. I will have a plot later. Okay, so I'm probably the last person go inside the detector. This is me. After the whole cleaning, we still have a few small pieces of papers attached on the surface, and we use this long tube to remove the piece of residue paper by hand. It's so sleepy on the internal surface, so we have to use this very strange position to support each other, and then we like in turn to this is me, and we switch and to do this job. It's quite energy consuming work. Okay, yes. Actually, there's another person, Yue Kun, is taking pictures for us. So there are 4 of us finally in the detector. Okay, so this is the top. Before we fill the detector, also during the detector filling, we are installing a bridge. Then this will support the top tracker. I will also mention it later. And this is the chimney where we do our scintillator filling and also do the calibration. And this is the installation of the calibration house. And Jiang Lai's group is responsible for this calibration system. So it's a very nice design and very nice work. And finally, all the specifications are met. And this is Shanghai Jiao Tong University team. And we have the 4 system calibration. This is the house, as already in the previous page slide. And we have one vertical calibration, automated calibration system to do the vertical calibration is 1 dimension. And we have 2 planes to have a 2D dimension calibration. Use the CLS system. It's a cable loop system. We can do the calibration in 2D. And we also have this remotely operated vehicle, ROV. This is like a submarine you can operate, and it can go anywhere inside the detector to do the 3D calibration. So in this case, according to the Monte Carlo, we can achieve a very good nonlinearity uncertainty and calibrate the response well. And this is a very new plot, probably a few days ago. Our liquid level is at roughly here, or even lower. So all these are the filled liquid designator, and we are going to complete the filling by August. end of the August. So we perform very comprehensive quality control and assurance program at every step of production, and also finning, like the transparency measurement and the radioactivity control, and also monitor the radon by a test facility. This is a 20-ton small detector to quickly monitor the radon to mini becquerel per cubic meter level. And we monitor the nitrogen, water, etc. And all these specifications are in good control. And when we fulfill the water, we operate, first time we turn on our PMTs, we see a nice chunk of ring from muons, so all the PMT works fine. We were excited to make these plots like a Super K to observe. We are almost a similar scale as Super K for our water pool, but this is from the internal. This is from our central detector PMTs, so the ring looks nice. Then we do the further commissioning. We monitor the dark rate of PMTs and do the gain study. And the dead PMTs was actually very few, much less than 1%. And we do found some flasher PMTs. This was not good. We know that for long history that the PMT can have some spontaneous flashing and produce light, and this light will be unphysical events, so which can cause background. Super K observe this, Diabe observe this, and JUNO we also see this. So we are working on how to reject them or turn off the PMT if they are too bad. For waveform, the noise is very good, and the trigger threshold, we can reach a very low level trigger threshold, 150 keV. We also have a software trigger system which can even go lower, like a 50 keV. This can be good for PP neutrino study. And the other performance for the liquid scintillator, the radioactivity are good, and from the radioactive sources calibration, the attenuation length of the scintillator is good, and light yield is exactly almost similar as what we expected in the Monte Carlo, more than 1600 per MeV. And they see nice peak, nice neutron peak from the neutron source. So all are in good shape, and we are excited to do the commissioning analysis and wait for the future data. So the scintillator production and purification, I kind of organized my slides in a sequence of our detector construction and the finning. And so when we do the commissioning, use water, and during the finning, then our liquid scintillator production continues. So this is the 5,000 cubic meter storage tank above ground to store the temporarily store the solvent, LAB. And then we go through the aluminum cylinder, a set of aluminum dioxide cylinder to do the filtration to improve the optical transparency, and then go to the destination to further remove the radioactivity, and also improve the transparency a little bit, and do the mixing with the fluorous wavelength shifter, and the primary solution is diluted with the solvent and then transport 1.8 kilometers underground to the underground in scintillator hole to do the water extraction, the other system to remove the radioactive impurities, and finally do the gas stripping to further remove the radon and the oxygen. And then before we finally fill into the detector, we need to monitor the transparency and also the low background meet our requirement. So we build this auxiliaries monitor system to further check the quality, and if it's fine, then we fill our detector. So this is the whole process. And in the meantime, we'll continue to do the installation on top of our detector. we have this plastic scintillator from OPERA experiment. When OPERA decommissioned, all their scintillator modules are in-kind contribution to JUNO, and this provides 60% coverage on top. This will allow us to have a very precise measurement of the muons. Even it's not 100% coverage, but still it will provide a well-calibrated muon sample for us to tune our reconstruction algorithm to further reduce the muon-related background. Now the installation, the bridge and the detector modules are all installed. We are doing commissioning right now. And these are from Monte Carlo, and the angular resolution and the position resolution are excellent. And this is a new plot, a few weeks before. The final installation of these TT modules are in place. And this gives you an overview about during the whole process, how we control our backgrounds. And we even have a hard time to control our radon in the underground tunnels. We have, you see, many different tunnels, and this is our location of our experimental hall. We have to control, we have a requirement on the experimental hall to have less than 100 becquerel per cubic meter radon. But usually in underground, the radon can easily go up to a few thousand becquerel per cubic meter. It's even harmful for human. So we have to do a good ventilation to design this a little bit complicated route of this ventilation design. And finally, the experimental hall, the radon level was reached to a good level. And we also do a careful screening of all different raw material to reach a good low background environment in our detector, less than 10 hertz of the whole 20 kiloton detector. And also a very careful control on the cleaning and the thinning. So I kind of spend more than half hour to explain the detector. Now I come to some physics sensitivities. I will probably skip or quickly go through some non-particle physics related topics, but I prepare my slides in a complete list so you can check later. Focus on the oscillation and measurement. So again, this plot, problem technologies. So I like this plot from Yifang, so I use it for several times. So in the end, I want to highlight that JUNO is a liquid scintillator detector. And you see this liquid scintillator detector can actually do a lot of studies. And then all these important problems can be studied in JUNO also. Okay, so now I first go to the oscillation parameters. I just show you some results, of course, based on Monte Carlo, the sensitivity study. So first is that with a 20 kiloton low background scintillator detector and powerful reactors, you can easily improve the oscillation parameters by a factor of 5 to 10. And very quickly, on 100 days, we can reach or surpass the direct measurement, as you can see here. The direct measurement is 2 to 5% level, and within 100 days, we can be better than that. And after 6 years, each of them can be like a 0.2 to 0.5% level, and this will provide us opportunity to test the unitarity of the mixing matrix. And also the reactor flux and the spectrum is important for JUNO. I did not prepare a specific slides for our satellite experiment, JUNO Tau. This actually was a satellite experiment near the Taishan nuclear reactor core. It's 40 meters from the core. And this detector is a ton-scale liquid scintillator detector, and with silicon PM coverage operate at a low temperature to maximize the light yield and also reach we expect to reach a very good energy resolution to measure the reactor neutrino spectrum, the shape. This will provide a model-independent reference for the main detector and also a benchmark for test the nuclear database. This plot shows you we expected to control the spectrum shape uncertainty less than 1%. And this is going on in parallel with the main detector. For neutrino mass ordering, this kind of a next step for after we do the oscillation measurement. This table, well, sorry, why it should like this? There should be some values, but well, you can check it later. But this table, I plan to show you the comparison between our original design in 2015 and the updated value. So some of them are toward the worst direction and some of them are toward the better direction. We carefully evaluated in the past few years based on our as-built detector. So in the end, we reach almost the similar sensitivity as before. The major factor is that the power plant, we have 2 reactors cores less due to the government regulation that was stopped a few, like 10 years before, well, a few years before, not 10. And so we are missing statistics by 25%, but we managed to compensate using other analysis techniques. So in the end, we reach similar sensitivity. For reactor only, after 6 years, we can reach 3 sigma, and now we are working on the combination with our atmospheric neutrino oscillations. We aim to reach 3 sigma even earlier and 4 sigma in 6 years. This is the plot show you how is the synergy at JUNO use the reactor and the atmospheric neutrino to improve the sensitivity. So this work is just started a few years before. We realized that actually the huge liquid scintillator detector has a great potential to measure the directionality and energy and even PID, the particle identification for flavors and for neutrino, anti-neutrino discrimination. So this was never realized when we write our yellow book, like in 2015. We did a very conservative estimation at that time, but now we think it can play a significant role in our future analysis. And also we can use the external delta square measurement from accelerator experiments to further enhance the sensitivity on mass ordering. Again, the challenges for neutrino detection in the GeV energy region. Our detector is like a camera, a big camera. You can take a snapshot of the atmospheric neutrino interaction, or it's a short movie because we do the waveform readout. For each waveform, we have 1 gigahertz for 1 microsecond, so 1,000 points. So it's a short movie. So based on this, using advanced AI technology, machine learning approach, you can do the spherical different model like deep sphere, point net, efficient net, etc. to do the reconstruction and the PID. So now we are working on this based on Monte Carlo, and in our interested region from 1 to 10 GeV region, the angular resolution is good. It's even better than Super K because Super K, in water, you never see the hadronic particles final states. It does not cross the threshold. But in liquid scintillator, all this information, the hadron informations are recorded. It's a complex pattern, but it's in the data. So if you only measure the charged lepton, your angular resolution between the charged lepton and the real neutrino direction has large spread. But in a scintillator, you can improve quite significantly. And that's the good thing for JUNO. And I forgot to have another plot that the PID is also very good. So we are now have the commissioning data, so we are going to verify this. Okay, for geoneutrino, I quickly go through the other topics. For geoneutrino, we have 20 kiloton, and the Camlin have 1,000 ton, so 20 times larger. So in 1 year, the JUNO data will surpass the previous Camlin Broxino measurement. And within a few years, we can have a very good measurement on the crust geoneutrino flux, and also probe the mental contribution. And this is an interesting multidisciplinary study between particle physicists and geological physicists, geochemistry, physics, etc. And for supernova, they have this diffused, first is the core collapse supernova burst. With scintillator, you can register all the flavors of core collapse supernova. Of course, in the MeV energy region from 1 to 60, for example. And we have the inverse beta decay, electron scattering, proton scattering, charge current, etc. All the spectrum can be measured. So we can do a model-independent reconstruction of the energy spectrum of all the flavors. And some phenomenologists study the the mass ordering and the absolute mass using time structure. The lightest neutrino will come earlier using, but this is quite model dependent. We designed an alert system to monitor the supernova neutrinos and archive the data. And for diffuse supernova, the key challenge is to suppress the atmospheric neutrino background. And with the PSD technique, we can make the signal stand out. And in a few years, we can reach a good sensitivity. For nominal model, we can reach 3 years, 3 sigma, and probably 10 years definitive discovery. And even we don't observe signal, we can put a limit on the flux. Probably I will skip the solar neutrino part. Again, good measurement. And also the use solar neutrinos to test the tension between the previous solar neutrino measurement and the reactor neutrino measurement, and do an independent flux measurement, just like what Snow did. And the nucleon decay, the key feature in the scintillator is that nucleon proton decay to kaon and neutrino, and this is a triple coincidence signature. So we are looking for the double peak signal in our waveform, and the background will be a single pulse. And again, the background, significant background is from atmospheric neutrinos, and the uncertainty is large. We should consider all different kind of hadronic processes and understand the final states. And we are even thinking about how to use the final state isotope decays to in situ measure the atmospheric neutrino background. And the sensitivity is here. It's probably slightly worse than hyper K, a few times worse than hyper K. This is another invisible nucleon decay search, so I will skip it. It's similar. So this table, I don't know why, but anyway, you can check the slides later. On all aspects, JUNO can do a good measurements. Primary goal is still mass ordering and CP phases. CP phases is not the target of JUNO, but the other two. So due to the limited time, in the next few minutes, I talk about the neutrino mass measurement. First is constraint from cosmology. This CMB distribution and a large-scale structure can provide total mass of the neutrino, three species of neutrinos, total mass, but it's highly model dependent. So every time in an international conference, they defend they have a stringent limit on the total mass, but we always argue that, oh, your measurement have model dependency, and we need definitive measurement on Earth to resolve this total mass. But you see this Euclid constraint that even they gave us more than 3 sigma total mass signature, but again, this is very model dependent. And they have their future targets, and this is a normal ordering parameter space, and this is inverted ordering parameter space. Okay, so for beta decay, this experiment, they have many different large scale and small scale experiments. I take the Katrin experiment as an example. So this beta decays. If a neutrino have mass, the shape at the end point will be different. And you probe this difference, you can measure the effective beta decay neutrino mass in this formula. And use tritium is the typical target, you can see here. The experimental challenges is the high intensity source, high reactivity source, and a very good energy resolution. You needed to probe the endpoint, very low background. So Katrin experiment built a very complex spectrometer and the system to handle the tritium molecules. And this fancy spectrometer, they used the magnetic Tesla scale magnetic field to guide the electrons from this end to this end, and use a spectrometer to measure the kinetic energy of the electrons. Their newest results achieved a limit of 0.45 electron volt, and this shows their history of their searching. This is the current best limit. They are also investigating new technologies to further push down the limits. For example, in Project 8, the target is reached to 40 mini electron volt in their next generation. And this another picture shows you the whole history from 40 years before to now, and the journey continues. Oh, this is the last part, neutrino is double decay. I come back to this concept that Marana proposed. The neutrino is own particle. This have a precondition that neutrino have mass. And in this case, you can observe this neutrino is double decay. In here is a monoenergetic peak, and the 2 nu 2 beta decay has the continuous spectrum. The challenge is you need a low background, high energy resolution, and searching for neutrinos double decay is very powerful, probably the only feasible probe right now on the Earth to probe the Marana nature of neutrinos. This is a no-lose game. So if you found the neutrinos double decay, you prove the neutrinos of Marana nature. This has been proved by the Shashitavale theorem in 80s. In this way, you can probe the absolute mass. And this will provide a process with the lepton number violation process. In this case, we can associate with the matter-antimatter asymmetry, where the matter particles can be created without antimatter. And by this process, you can probe the Marana phases. So here, this plot shows you the past experiment and the next generation. So the past experiment, these are our next generation, but past experiment is even above. This is next generation, different proposal, and with their accompanied current running experiment. Again, further explanation about this no-lose game. If you look at this 2D plot, if normal ordering, this will go infinite. There's no chance, seems no chance to measure the WL But if you do a very careful numerical calculation, you will realize that it's not a solid space, but it's like an empty space. You have this hole inside, and the allowed space, parameter space, is in circle. So if your future sensitivity can reach to 1 milli electron volts, you have a large chance to probe the lightest neutrino mass. So that's the dream for this neutrino instability decay. And the JUNO, after its mission on neutrino mass ordering, we can load the isotope in the center and turn it into a neutrino stability decay experiment. And this is a further explanation about how you can constrain the lightest neutrino mass, even the Mariana phases. And this is the aim sensitivity of JUNO. Okay, so probably I can skip this one. Just highlight the challenges is the background and also the doping technique. Now we are at the ton scale. The world is planning a ton scale experiment, but we should think about the future with 100 ton or even 1,000 ton scale. When I retired, probably I will finish the ton scale, but for your generation, it's 100 ton scale. Okay, so last slide. The nuclear matrix element in this formula is also an important thing. I think Russian scientists have a good background history on nuclear science, so probably some of you can help to resolve this uncertainty due to the nuclear matrix element. Now it's a few factors variation. If this can reduce, it will help a lot for experimentalists. And there are many ways to try, ongoing to try to reduce the uncertainty. So my last slide, sorry I was delayed. Thank you.
Thank you. And now we have time for just a couple of quick questions. Yes, please.
Okay, that was a question. And for double decay to be observed, we need just a decay to be forbidden. And is there possible materials for double beta decay candidate is smaller? So what are the optimal candidates for the double or neutrinoless double decay?
The optimal candidate, sorry, I don't have a back slide. The current, on the market, we have several isotopes, like xenon, germanium, tellurium, even, 钙怎么说? Ca, calcium, yeah. So the requirement is calcium, Ca, 48, yes. All these isotopes, they are single beta decay forbidden, but allow a double beta decay. So the requirement is that they have a high Q value to suppress the radioactivity, and also you have to be able to make ton scale detector. So this is the most challenging part. For xenon, it's easy to scale, relatively easy to scale up. For germanium and the tellurium, you need to make it into crystals. Well, making crystals is, and super clean crystals is not easy. Now Legend is using germanium, and Kupit experiment in Gransasso is using, it was used tellurium, but now use the Mananium, no? Yes, Mananium 100. And I don't know how to spell it, but MO 100. And then Snow Plus used the tellurium, tellurium 130. So these are all the possible targets. Beyond that, it's really difficult. I mean, to make it scale up to ton scale. Yeah, thank you.
Thank you. Any more questions?
Thank you for your lecture. I want to ask why we use free neutrino mass state concept? Like, why can't we assume that there are 4 or 5 states of them?
Sorry, yeah, when too fast. What's?
Why we use free neutrino mass state concept? Like, why can't we use 4 or 5 states?
4 or 5 states.
Why people measure only 3 neutrino mass, not 4 or 5?
3 neutrino mass. Oh, why only 3 neutrino mass, not 4 or 5? Okay, to current standard framework, we only know 3 type of neutrinos participate in weak interactions. That's the way to study the neutrino. People talk about the sterile neutrino, which don't participate weak interaction, but they can participate in flavor transition and also the propagation. But this was not never. Well, we have many experiments looking for sterile neutrinos, but currently no evidence yet.
You talk about flavors, so the mass states are connected to flavor states?
Yeah, the mass eigenstates, well, when it propagates in vacuum or in matter, it propagates in mass eigenstates. But you have to detect it. When you detect it, it behaves in flavor states. I'm not sure if I.
Thank you for your presentation. Maybe I have a few questions. Could you please turn to page 37?
37.
This page. Could you explain more about this, the right bottom plot with the second peak?
Second peak.
I'm not sure if it is physics precise.
Yeah, this is a neutron capture on carbon. We have our is organic solvent, so we have a proton and a carbon. So they also have a small cross section on carbon capture. Yeah.
And then could you please turn to page 48? For the reconstruction, so I mean, in JUNO there will be 3 different kinds of PMTs with different size, different TDS, different quantum efficiency.
Yes.
For the reconstruction, I'm wondering how will you decide the photons received by different PMTs?
How we decide the photons received by different people?
Or certain situation, maybe there are different or nearby PMTs receive a different number of photons. So how will you decide these photons to reconstruct the direction, the energy?
Okay. So we have a 3 PMT system. You can imagine it's like a three cameras. Mm-hmm. They all look at the same events.
Yeah.
So you register the different heat pattern, charge pattern, time pattern, whatever, 3 different pictures.
Yeah, I mean, as I know, if we want to reconstruct the direction, if we have like photons with the quick time resolution, maybe we will have better reconstruction result. So,
yes.
So with with like 2 different large PMTs, the TDS is quite different.
Yes.
So how will you decide these 2 kind of photons in these PMTs?
I think for reconstruction with them, or we use all the information. We don't distinguish PMT by PMT. We use the whole pattern to construct a sort of likelihood, or do this pattern recognition to reconstruct the energy vertex track, whatever. We don't distinguish PMT by PMT.
And maybe another question for the PMT dark noise, because I think if we receive the photons like in JUNO, maybe different PMTs will have different PMT dark noise.
Yes.
So for the reconstruction, we will do some like trigger or data cleaning for these photons to receive more wavelengths?
Yes, that's the difficult thing we are working now to reduce the dark noise impact on energy resolution. If it's beyond the signal window, it's easy to reject. But if it is coincident, inside the same signal region, it's very difficult. So we are now doing some advanced machine learning technology to try to identify some hits from dark noise to improve, but it's difficult. Yeah.
Thank you.
Well, we need to proceed with our program, so let's think of
Thank you.
Thank you.